brain tumors. We are going to compare different radiosurgery techniques and machines for our brain tumors: GammaKnife, CyberKnife, ZAP-X, and HyperArc. So first, please let me introduce our moderator today. So our moderator is Professor Byungchul, professor from the Department of the Radiation Oncology of Asan Medical Center, University of Elson College of Medicine. Professor Cho was currently is the vice president of the Korea Society of Medical Physicists. She also is the board certificate of the Korea Society of Medical Physicists. Internationally, he's a member of the Astro too. He has been published more than 60 papers, scientific papers. So, Professor Cho, I will hand the microphone to you. Thank you.
Thank you, Jin. Hello everyone. Today we will we'll have the 4 guest speakers. They are talking about the navigating the landscape of brain tumor radiosurgery. So first, GammaKnife will be covered by Professor Hyun-Tai from Seoul National University, Korea. And secondly, HyperArc by Professor Hae-Jin from Aju University, also Korea. And third, CyberKnife Radiosurgery by Professor Hojin Kim from Yonsei University. And last speaker will be covered ZAP-X, Professor Andreas Mack from Swiss Neurosurgery Center, Switzerland. So hopefully this talk help you to understand basic physics of radiosurgery and also clinical applications. So let's start with the first topic, GammaKnife. Let me briefly introduce Professor Hyun-Tai Chung. He finishes his PhD experimental nuclear physics at Seoul National University in 1995. After then, he joined that Department of Neurosurgery at Seoul National University. And he have been work more than 25 years from then. And he also served for many years as board members of Korean Society of Medical Physics. And also he was president of Korean Radiosurgery Society. So clinically, he's covering GammaKnife. So he has very deep and well-known experience and knowledge about GammaKnife. So he also achieved many scientific papers also. So today I'm expecting his very wonderful talk. So welcome, Professor Hyun-Tai Chung.
Okay,
if you are ready, then yes.
Can I show? Okay, I will try to show my slide. I hope you can see my slide.
Yes.
Okay, so let me start. So welcome everybody, and thank you, Mr. Chairman, for nice introduction. I want to thank you all for showing interest in radiosurgery, which I have serviced for 27 years. As you know, today's subject is the measurement of brain tumors with radiosurgery, and my part is GammaKnife surgery. For this subject, I think we need to start by understanding why we use radiosurgery for brain tumors. So I will explain why we perform radiosurgery for brain tumors, then a brief introduction to GammaKnife surgery will follow, and then I will show some representative examples, clinical examples, VS, meningioma, pituitary adenoma, and brain metastasis. Then, finally, I will show quality assurance activities to guarantee GK's excellent result. So let's begin. Here in this MR image, you can see this enhanced tumor. It looks terrifying. It might be a glioblastoma or brain metastasis. And we want to treat this tumor without opening the skull, and nor we don't want to harm the normal brain tissue around this tumor. So one possible way is to give radiation from the outside, is external beam radiation. But as you know, there is some problem with external beam radiotherapy. When we give radiation from the right side of the patient, like this, the normal tissue from the skin to the target gets more radiation than the tumor itself. It's a problem. But we also know that there is a solution for this, the fractionation. The 2 gray per day for 30 days is not equivalent to 60 gray in a day. Thanks to FOR, I guess you already know this. So this fractionation works for high alpha beta tumors thanks to FORs. So it's good for fast growing malignant tumors such as cancers, and among the brain tumors, the malignant brain tumors like glioblastoma, anaplastic meningioma, and brain metastasis are good candidates for fractionated RT. But there are benign brain tumors. They are very slow growing tumors, and their alpha beta ratio is low. Usually we say 2 or 3, but some people say it is lower than 2 or so. Like here, you can see the vestibular subanomal and meningioma and pituitary adenoma. So what can we do for these benign brain tumors? How to irradiate the benign brain tumors? That's the question. We know that we cannot apply this fractionated radiation to benign tumors. There must be another solution, and it is simple. Just give more radiation to the tumor than the surrounding normal brain, like this. It means we focus the radiation only on the tumor with this radiosurgery. So in this radiosurgery, we don't need 4 hours. We just want to kill everything inside the radiation field. That is radiosurgery. So now, naturally, only benign brain tumors can be major indications of radiosurgery. For example, vestibular subanomal, grade 1 meningioma, pituitary adenoma, and other low-grade tumors. And in addition to this, we can apply radiosurgery for vascular lesions and functional disease. And also, we often apply radiosurgery for brain metastases, though they are malignant tumors. I will come back to this region. I'll come back for this region later in this lecture. So let me briefly summarize the difference between RT and radiosurgery. Compared to RT, the radiosurgery does not rely on 4 hours. So the radiosurgery is performed in principle as in a single session. Because of this, major indications are different. RT is good for fast-growing tumors such as cancer and malignant brain tumors, but radiosurgery is good for benign tumors and vascular lesions. Now we know why we use radiosurgery for benign brain tumors. Then it's time to perform a radiosurgery. For this, first thing we have to do is to see and locate the tumor. Then we need to focus the radiation, then plan how to adjust the radiation to the tumor. Then we fix the patient and irradiate. Very simple. This is the typical procedure of radiosurgery. So the first thing is to find where the tumor is. For this, we need to set the coordinate for ordinary MR or CT images. The conventional way is to fix a frame like this one to the patient head. When we take the MR images with the indicator on this frame, we get the 6 fiducial markers like this. Then we know where the tumor is by measuring the distance from the fiducial markers. It's very easy. But the frame is a kind of painful device. So these days, this mask fixation is preferred. The center of this CT image is adjusted to the center of this machine. So when you take the combined CT images, we know the coordinates for each pixel. So we can use this indicator with frame or a combined CT of GammaKnife itself. Once we know where the tumor is, it's time to focus radiation on it. There are several ways to focus radiation, and this is the one distinguishes each radiosurgery machine. The leftmost figure shows the principle of GammaKnife. The cobalt-60 sources are distributed around the patient head, and all the beams are adjusted to meet at the focus. Each beam is weak enough not to harm the brain, normal brains on the path, but when the beams meet at the same point, the intensity becomes 200 times higher, and we can treat the tumor. Other experts will explain lineup, CyberKnife, and ZAP-X later. So this is the latest model of GammaKnife, GammaKnife S3. It looks a little bit different, but the radiation part is the same as to its previous model, GammaKnife Perfection and GammaKnife Icon. The sources are on this conical surface, and they can move back and forth to be on the collimators. There are 3 different kind of collimators, 16, 4, and 8. The source can be moved on each of them. And this is the patient couch to set the tumor to the center of the machine, to the radiation focus. It's a very simple machine. Now we know where the tumor is and we can focus the beam. Then it's time to plan how to adjust the beam to the tumor. The building block of this planning is so-called the shot. When you see some certain level of radiation around the center, you can see some elliptical surface like this, and we call this as a shot. There are 3 different ones, 4, 8, and 16 millimeters. We use small collimators for small tumors and large collimators for large ones. The treatment planning system for GammaKnife surgery is Lexel Gamma Plan. Here is an example of treatment planning made by Dr. Novotny Jr. And the red one is the vesicular schwannoma. And by arranging the location, size, and radiation time of each shot, we try to cover the red tumor with yellow radiation. And this is the final plan. Now the plan is ready. So it's time to fix the patient and start to irradiate. The conventional way to fix a patient is using this frame. This is good because the patient head does not move during irradiation. So it's very good for us, but it's very painful for the patient. So patient prefer this mask system, and you are very familiar with this mask, but everyone knows that the patient head can move under the mask up to several millimeters. So during irradiation, we monitor the patient head, motion of the patient head by using this infrared system and a reflective marker on the nose. So after irradiation, we can send the patient to home. This is the typical procedure of radiosurgery at Seoul National University Hospital. Early in the morning or the night before, the patient take MR imaging, and on the day of radiosurgery, we make treatment plans using these ordinary MR images. When the plan is finished, we call the patient and put a frame or make a mask. So the patient is fixed to the GammaKnife machine. Then we take a cone-beam CT image. This one has stereotatic coordinates. So when we register the ordinary MR image or CT to this cone-beam CT image, we will have stereotatic image and we can start radiation. The radiation is performed by this machine automatically. We just push a button and watch the patient. After the irradiation, we can send the patient go home. It's a very simple procedure. So now we know the whole procedure of GammaKnife surgery, and let's take a look at some clinical examples. Before we dive in, let me tell you one thing. I will give some information on the indication criteria and clinical results and those descriptions, but they are just a general information, not the absolute one. So some people may use different polish or values at some different cases, just some examples. And the first case is a vesicular schwannomas. This is the most representative indication of GammaKnife surgery as a benign tumor. It is common to confine the tumor not too big for radiosurgery, and the prescription dose are 12 gray or 13 gray depending on the patient hearing status. And the 10-year local control rate is higher than 95% and many size. And schwannomas, including vesicular schwannomas, show transient volume expansion usually between 6 to 8 months after GKS. This is one of the best example of vesicular schwannoma. There was a 3.3 cubic centimeter tumor here, and GammaKnife was performed. Then tumor continually shrank, and 5 years after the GammaKnife surgery, it became 0.8 cc. This is very happy case, actually one of the best case. Oh, sorry. How come? Oh, I'm sorry. I just pushed my space button of my keyboard. I'm very sorry. And this is the second case of VS patient, a 43-year-old man with tinnitus. The tumor was 9.1 cc, a rather big one, so we reduced the dose to 11.5 gray. The patient hearing was 36 decibel with 90%, it means serviceable. But after 6 months later, the GammaKnife surgery, the tumor increased to 12.2 cc and the patient lost hearing, unfortunately. And at 1 year after, the tumor was still bigger than GammaKnife status, GammaKnife time. But 2 years after, it reduced to 8.7 cc, and 4.5 years after GKS, the tumor reduced to 5.3 cc. This kind of temporal expansion is very common for GammaKnife surgery with schwannomas. And the next example are meningiomas, intracranial meningiomas. It is one of the most slowly growing tumors, brain tumors. We also limit the tumor size depending on its location, and the dose of 11 to 15 gray are usually described. And it is often sees more than 93 tumor control rate in 10 years at many sites, and many tumors remain stable rather than shrink. And this is a 48-year man with a diplopia. His tumor was 4.7 cc. We prescribed 11 gray. And 9 months later, the tumor reduced to 3.9 cc and the symptom disappeared. He was neurologically free, very happy. And the tumor continually shrank to 1.5 cc at 40 months after the GammaKnife surgery. But this is one of the best case again. So most of meningiomas does not shrink, it remains stable. The second example of GammaKnife surgery for meningioma is a 57 years old female with mild headache. One of the common complications after GammaKnife surgery for meningioma is edema around the tumor. About 15% showed brain edema after GKS, and about half of them are symptomatic. The symptomatic edemas are treated with steroids, and most of them disappear maybe 2 or 3 years after GammaKnife. This one had a 5.9 cc tumor here. We prescribed 19 gray. This case was in 1998. It was the very early stage of our experience, so we gave too much dose, we think. Maybe we do this in these days, we reduce the dose to 13, maybe 14 gray, usually 13 gray. But because we described too much gray, she complained severe headache. So we took the MR image 9 months after GKS. We can see the severe brain edema around the tumor. So the doctor prescribed steroid, and 3 months later, the edema was reduced very much and the symptom disappeared. And 17 months late after the GammaKnife surgery, now the tumor is only 2.3 cc and the patient is happy. But she suffered from severe headache due to this edema. And the third tumor is the pituitary adenoma. The primary treatment option for pituitary adenoma is endoscopic surgery, a transsphenoidal approach. The GammaKnife surgery is performed mainly as a residual or recurrent pituitary adenoma treatment. For non-functioning pituitary adenomas, we give around 13 to 16 gray. And for functioning tumors, we prescribe 20 to 30 gray to control the hormone level. The tumor control is rather easy. More than 95% tumor control rate in 5 years is very common around the world. Many tumors shrink, but the endocrine remission rate for acromegaly or other functioning pituitary adenomas are usually not more than 50%. This is an example given by Dr. Sheehan. This is the pituitary adenoma causing Cushing's disease. And at the time of GKS, it was 3.3 cc. And 6 years after the GammaKnife surgery, the tumor was reduced to 1.9 cc. The hormone was returned to normal level. Very happy case. Now we have brain metastasis. Brain metastases are fast-growing malignant tumors metastasized from primary cancers. There are several treatment options from surgery, orthogonality, chemotherapy, and immunotherapy. And earlier in this presentation, I told you that radiosurgery is unsuitable for malignant tumors. Then, why do we perform radiosurgery for brain metastases? It is because the ultimate goal of radiosurgery for BMs is not to eliminate the tumors. Of course, small BMs, for example, smaller than 0.5 cc, are often disappear after GKS, but larger tumors usually recur Actually, most of them recur. The goal of radiosurgery for brain metastasis is to elevate symptoms caused by the mass and to improve or maintain quality of life while the patient is alive. In addition to this, the brain metastasis can be easily delineated because it is well enhanced usually, and unlike gliomas, there is no infiltration to brain outside the tumor. So we can easily perform radiosurgery for brain metastasis. Again, GammaKnife surgery is applied for tumors smaller than 4 or 5 centimeters. Hypofractionation is often selected for tumors larger than 2 centimeters. In principle, there is no limit on the number of brain metastases, but whole brain RT is recommended for numerous masses. Usually 15 to 23 gray is prescribed. The median tumor control rate is 10 to 12 months, and the median survival period is 12 to 18 months. And most patients expire due to primary cancer. And here is 57-year-old man has a metastasis from a renal cell carcinoma. At the time of GKS, he showed a left hemiparesis due to this severe edema around the tumor. The tumor was 7.3 cc and 15 gray was prescribed, a little bit smaller than our current Polish, but happily enough, the tumor began to shrink. And 6 months after the GammaKnife surgery, the tumor becomes 0.8 cubic centimeter, and the patient showed no symptom. Very happy. But at 31 months MR, the tumor increased to 1.4 cc, and the patient said he had some left side weakness. But 3 months later, he expired due to lung metastasis. This is the typical procedure of GammaKnife surgery for brain metastasis. We cannot eliminate the tumor, but we can help the patient to live normal, ordinary life during he is alive. Okay, as we have seen in this example so far, GammaKnife surgery is very effective in management of brain tumors. You can see in this slide, about 90% to 50.6 and 36 is 87.1% are brain tumors in the indications worldwide in 2021. Benign tumors is 36.5%, and malignant tumors are 50.6%, and most of them are brain metastases. And this slide shows the changes in case mixes from 1991 to 2021. Light blues are benign tumors, and this green are brain metastases. This gray one are malignant brain tumors, and this purple is vascular lesions, mainly AVM, and this one is a functional disease. As you can see, the proportion of brain metastasis is keep increasing, and now it's about 50% of all brain, all indications. And the proportion of these benign tumors rather stable, and it takes about 35% these days. And by the end of 2021, more than 1.4 million or around 1.5 million GammaKnife surgery have been performed worldwide. Until now, I have demonstrated the effectiveness of GammaKnife surgery and its widespread use worldwide. But there is a question: is GammaKnife surgery almighty for brain tumors? The answer is, of course, not. There are some limitations. And the first limit is that there is a size limit. We usually say it is 3 centimeter diameter. It is because the complication rate gets higher as the tumor increases, and it becomes unacceptable around this size. Suppose there is a 1 centimeter diameter tumor and 10 normal cells are around the tumor. When the tumor increases to 3 centimeter diameter, there will be 90 normal cells around the tumor. It means 9 times higher risk of complications. So we have to limit the size of the tumor. We can apply gamma knife surgery. And these days, there's one possible solution. So many people try hypofractionation for large tumors. The second limit is when the tumor is close or adjacent to the critical organs like optic chiasm or within some important organs such as brainstem, we cannot use, it is difficult or impossible to use radiosurgery for this one. The maximum single dose to the optic pathway is set to be 10 gray, and it is related with 1% complication risk. And the maximum single dose to brainstem is 12.5 gray combined with 5% risk. So again, people try hypofractionation for these tumors these days. The third one stems from the fact that it takes time for tumor shrinkage after gamma knife surgery. So when there is some acute symptom requiring emergent release, the tumor resection is recommended rather than gamma knife. So you have to try to avoid gamma knife surgery on tumors with rapidly progressive symptoms. Okay, it's time to look at the gamma knife as a medical physicist. Until now, we have seen the clinical examples, but from now on, I will talk about the quality assurance activities of gamma knife machine itself. So, in the quality assurance of gamma knife surgery, there are radiation-related factors like mechanical accuracy and dose distributions and dose rate measurement. And among the image-related factors, I will mention only the accuracy of image co-registration for mask-based system and overall accuracy measurement. I mean, end-to-end test with phantom and CT images will be given. And in addition to this, mechanical problem or radiological problem, the patient can move during the mask-based gamma knife surgery. So I'll give brief introduction, a brief explanation how to measure the accuracy of the patient monitoring system. Let's start with the accuracy of the radiation focus. It means that we check the conformity of the mechanical center and the radiological focus. The vendor provides a special tool like this. After we set a film here and we push the button, then there is a marker on the film, which means the mechanical center point of the machine. Then we irradiate the film with a 4mm colorimeter. Then we have these images, and we analyze this film. And there's a sharp valley here. This is the mechanical center, and the center of this peak is the radiological focus. So this mechanical center and this radiological focus must coincide. So I did many times, checked. At the center of the coordinate system, 100, 100, 100, the three-dimensional error was 0.09 millimeters. And when we move the couch to an extreme position, 40, 160, the three-dimensional error was 0.06 millimeters. This is very accurate. We can say it is a very accurate machine. The patient couch moves with very accurate way. This graph shows the 4 measurement result for this radiation focus accuracy. We can see they keep within 0.1 millimeter level for 1.5 years. And there is another tool, a more simpler one, to check the mechanical accuracy, in a simpler way. There is a diode detector at the center of this tool, and we check this radiation dose distribution with this diode detector every working day. And the center coordinates in the X, Y, and Z were measured automatically and give how much error he found. So during the last, no, not last, it's a long time ago. So during the 1.5 hours, the mean offset was only 0.1 millimeters. So very stable machine, we can say. And the measuring dose rate of GammaKnife is one of the hot issue because it is a small field dosimetry. GammaX solid water phantom, like this one, is used. And the PTW 31010 is the main chamber I use. I also have some other chambers. And electrometers and thermometers and barometers I used at the standard laboratory level. And repeated dose rate measurement is measuring the half-life of cobalt-60. So I fitted my data with an exponential decay curve, and I got a value of half-life which is very close to the known values. So we can say the measurement system is working consistently, at least we can say that, but we don't know how accurate the value itself is. It's another problem. So to solve that problem, in 2017, the IA published technical report series 483 for small field dosimetry. And in this report, they define a reference field for each device. For GammaKnife, they say 60 millimeter collimeter field is a reference field. And they also introduced a correction factor. I call it MSR correction factor. But unfortunately, several minor things need to be corrected in description of GammaKnife reference field in TRS-483. Most of all, the source to surface distance cannot be a single value for spherical phantom. The sources are on the surface of cone, and phantom surface is sphere, so we cannot define a single value. And the field size is not 1.6 or 1.8 centimeter for type C model. It's just 16 or 18 is the name of the collimator. The field size defined as a pole width at half maximum is slightly larger than their names. Anyway, it is not important. The important thing is the correction factor values. So I checked the dose rate of these 3 ion chambers before and after correction. For correction, I used the TRS-483 recommended values and other studies and averaged values. And this graph shows the dose rate, relative dose rate of these 3 chambers before correction. They are not constant at all, but when we apply the average correction factors, these 3 chambers produce the constant values, at least statistically constant values with p-values of 0.65. And even though the TRS-483 was a little bit worse than average value, it also produced very good results. And regarding the dose rate of GammaKnife, there is another factor called collimator output factors. The collimator output factor is the ratio of the dose at the center of a collimator to that of the those at the center of 60 millimeters. Some people say it is collimate out factor, the other one says Hellman out factor, and it is field out factor in many cases. And the Lexel gamma plane, the most recent one, use 0.814 for 4 millimeter and 0.9 for 8 millimeters. And it's a very interesting task for medical physicists to check these values experimentally. So the most intrinsic problem in small field dosimetry is that the dose distribution is not flat inside the detector. So the measured value is always smaller than the dose rate at the maximum point, and we call this as the volume averaging effect. To account for the volume average effect, we developed a very interesting, detector, scintillating detector shaped just like the dose distribution. So we can calculate the volume averaging effect very easily, just add and divide. And this one is the actual scintillator. It looks, something like a cube. Anyway. And this graph shows the collimator out factors reported from 2009 to 2022, our work. The output factors, I didn't do this, okay. The out factors of the 8 millimeter collimator is decreased from 0.92 or 0.93 to 0.9, which is very close to the gamma plane value 0.9. But the output factor of the 4 millimeter collimator is kind of keep increasing. And the recent values are 0.826 in our case, are slightly larger than the gamma plane value. It is 0.814. So there might be some necessity to change these values, but it's not my work. Okay. And usually the dose distribution is verified by measuring the full width at half maximum and the parabola in the one-dimensional dose distribution. But I think I'd like to use the gamma index pass rate in two-dimensional dose distributions. And when I apply 1 millimeter 3% criteria, almost always I got the gamma index pass rate larger than 99%. It's good. But we can check the gamma index pass rate in more realistic situations. So I used radiosurgery phantom CI R605, and I set the films at 5 different configurations: anterior, bottom, mid, top, and left. And 2 or 7 images at each configuration were obtained. And I also used 3 different multiple shot plans like this, A, B, and C, and total of 93 films were analyzed. These 4 graphs shows the global gamma index pass rate. Graph A is for different size collimators, a single shot is almost 100. And B is for the different planes, actual coronal theta, again, the single shots. I'm sorry, the multiple shots. And C and D shows the dependence on top, bottom, anterior, left for all multiple shots. And this is for the actual clinical plan. This top position is little better than, little worse than others, but anyway, the mean gamma index pass rate under 1 millimeter 3% was 98.6%, which is very good for me.
Professor Chung,
Yes.
sorry for interruption, but could you summarize in maybe few minutes?
Yes, of course. Don't worry.
Thank you.
How much? Oh, sorry. I'm sorry. I will speed up. So I checked the image code registration accuracy. This is a PDC mark based system we obtained with University, and this is a Conbeam CT based system obtained with Conbeam CT. Before we correlated this image, there were already 0.46 millimeter differences. So after we correlated this CT image to Conbeam CT images, we will have another 4 registered coordinate. We compare these two. Then this graph shows the 1-dimensional difference and 3-dimensional differences. When I did not move the phantom, the difference reduced from 0.46 to 0.34, but it is not the clinical situation. In clinical situation, patient move during Conbeam CT and again, CT and Conbeam CT. So I moved the phantom very, large, motion, but it becomes a little bit larger, but still acceptable. And the end test for positional accuracy was performed. The result was 0.6 millimeter for frame-based system and 0.5 millimeter for mask system. Dr. Mack did this long time ago, it's 22 years ago with MR images, and his result was a little bit better than me, but I want to insist that my results are agree with his result within experimental errors. Thank you, Dr. Mack. And final one is I checked the high definition motion measurement system I made this tool with tape and rulers. It looks ugly, but it worked very well. I adjust the motion of this tube with depth micrometers, 0.05 millimeter accuracy. And this one shows the relation between high definition motion measurement and actual relation. The slope, the proportional slope of this was 1.00 and 1.00 for X, Y, X and Z direction. It looks very good. So this is my last slide. I can say GammaKnife surgery can be performed with sub-millimeter accuracy. And GammaKnife surgery can control benign tumors, benign brain tumors with usually more than 90% long-term control rates. GammaKnife surgery is one of the prime options for brain metastasis, even though it is a malignant tumor. And tumor size is one of the major limiting factors for GKS, and hypoplastic GK is being performed. And the symptoms or hormone levels may not be improved after GKS, even though the tumor is controlled. Thank you. Thank you very much.
Thank you, Professor Chung. Thank you for your excellent talks and very good for introduction. And I will collect the all questions. Please use the chat button, bottom of the Zoom link. So at the end of the 4 talks, I'll come back to you with the collected questions. But briefly, just one question to Professor Chung. So you mentioned about the co-registration accuracy, image accuracy. So I'm thinking the slice thickness of the CT or Conbeam CT. So I guess the resolution is close to that your error. Is that right?
That's a very good question. The slice thickness was 1.25 millimeter for CT images, and it's 0.5 millimeter for Conbeam CT images. So,
okay.
So it has intrinsic error range with this, but I have to give some values. The coordinates is given by interpolation in the GammaKnife, in the gamma plane. So even though you have 1.2 millimeter thickness slice, they can put the coordinate for each coordinate pixel. So we can calculate the errors. But we must always think there is some slice thickness in the images. Yes, it's a very good point.
Okay, thank you. So we are moving on the next talk. So the second talk on HyperArc will be presented by Professor Hae-Jin Park. She obtained her PhD from the Catholic University of Korea in 2014. She began her clinical career in actually 2009 at the Department of Radiation Oncology, Aju University Hospital. She have been worked after then, and since 2022, she has served as a clinical associate professor. And Professor Park has been various research work achievement, and as a clinician also, she has given numerous invited talks and presentations and publication, and also patents. So currently she's Varian HyperArc consultant, and her department is Varian HyperSite Reference Center. So I'm expecting she's one of the best knowledge about HyperArc treatment. So welcome, Professor Park, and if you're ready, you can start.
Okay, can you guys see my screen over there?
Yes, yeah.
Okay, let me start. Thank you, Professor Joe. Thank you for kind introduction. Good afternoon, everyone. Thank you all for taking time to join for Saturday webinar today. Again, I'm Hae-Jin Park, and I'm serving a clinical medical physicist at Aju University Medical Center. And also, I'm a Variant HyperArc International consultant as our various partners now. It's my greatest honor, and thank you AFOMP school committees and the Professor Joe for giving me opportunity as a speaker today. Before my lecture, Professor Chung delivered an excellent talk on the effective treatments for brain tumors using the GammaKnife. It is a very traditional way to treat the brain tumor worldwide. But so today, I'd like to introduce the HyperArc, a Xeon-based Linux technique for treating the brain tumors and multiple metastases. I will go through the workflow in AUMC, and also I would like to share my experience and about the planning tips and QA solutions. So by the end of this talk, I hope to provide you with a deeper understanding of HyperArc techniques for brain tumor and share some practical insights that you can apply in your clinic. Okay, before we dive in, let me talk about the AUMC very briefly. Aju University is located about 30 to 40 minutes from the capital of the Seoul cities in Korea. We are currently treating over 200 patients every day now. And our team includes 6 radiation colleges and 3 medical physicists and 16 RTTs. We are all working together now. So in our departments, we got 4 machines up and running now, and we are really excited about the new additional Halcyon HyperSonic mission at the moment. We've also upgraded both Eclipse and ARIA server to the latest version 18, which let us use all of the new features together now. On the top of that, so we have a license for the HyperArc, MCO, and repeat plans. And also we are running a Velocity and Mobius and Citrix server, and also the GPU fast server, things like that. We recently applied an SDRT solution to the patients with a LineRT system. So as you can see, most of our operations use a Variant product. So I'll be sharing my HyperArc experience in Variant environment today. So we are actually really lucky to be the first site in Asia over the years. For example, we were the first HyperArc site in 2017, and we recently achieved the same with the HyperSite earlier this year. So now we are operating as a HyperSite reference center now. As a first site, we've done many activities such as invited talks in many places. So we also serving a HyperArc consulting 3D variant if the customer installed the HyperArc at their institution at first time. So some of you in the audience might have attended my previous lecture or not. If they're the case, I hope this serves as a helpful reminder. So here is our HyperArc installation timeline. We started the HyperArc installed Trubim in November 2017, and in February 2018, we visited the second HyperArc site in worldwide, the Byungchul Cancer in England, for training and discussions. Finally, in March 2018, we treated HyperArc for the first time in Asia. So what is the HyperArc? HyperArc actually has been released in 7 or 8 years ago, so I'm sure many of you are already familiar with it. Its conceptual aspect and are actively using it in many institutions. However, before I explain our institution's workflow, I'd like to briefly go over the concept. So what is the HyperArc prerequisites? Which option should we take into? So actually the HyperArc requires Trubim or at 2.7 version or higher. And also 60 couches is required, and the high intensity mode energy is also required. For example, the 6FFF or 10FFF. And also HyperArc should be used the new type of mask, which is called the QFix in-campus SRS immobilization system. And also we are selectively use 2 different type of MLC for Millennium MLC and HD MLC as an optional. For software, the Eclipse version 15.5 is required, and for the ARIA server is required for the 15.1 or higher one. And you may think additional option if you do not have any SRS QA devices for the patient and machine, and which modalities will be used in the future. So you guys have to think about and consider about these options in advance. So HyperArc can define very, actually define the workflows. It provides, fixed geometry up to the 4 arcs. And HyperArc can allow the users to automatically treat treatments with a single click. And it enables efficient SRS treatments. It is about the 20 minutes only. And this allows us simultaneous multiple metastasis treatments with a single eye centers. It has compact target dose and steep dose gradients than existing repeat treatments using the new algorithm in HyperArc. And also, the patient safety issue can also be taken account into the system using only the safety trajectories. So from now on, I'd like to talk about how to set protocols at AUMC and how to apply this HyperArc technique to patients. So looking at our process of the HyperArc at AUMC, so basically we keep the treatment's preparation taking 2.5 days to 3 days, and we set the treatment to go in on first day actually. On the first day, we are acquiring the CT and MR images, and the physician defined the tumor on the same day, and we did a plan on next day. And the day 3, we get a confirmation by the physician and proceeded with the patient DQA. And on the day of the treatments, we are finally doing the mechanical QA during the QA slot for about 30 minutes before the treatments. So we didn't actually reduce our current protocol so far. This is because even with these settings, we very often had to prepare the shorter treatments depending on the clinical situation. So now I will go into the detail about the preparation process for each stage. So this is the first day of the procedures. As I mentioned earlier, we did image acquisition and target contouring at day 1. So the HyperArc actually recommends a MRI fusion for target definition. So we share the same MRI slot with the GammaKnife team at 7:20 a.m. And we ask them to scan similar HyperArc condition as much as possible for the image fusions. We are also getting a CT scan with a 1 mm slices, and the CT scan must be include the minimum of the 7 cm from the end of the frame and up to the shoulder parts. It can be calculated by the system, and you can get more information about the collision in advance. And also, we are using the QFix couch frame, which can replacement like this video. And also, we apply the QFix in-campus mask for the patients, and this is actually mandatory for the HyperArc. So additionally, we can selectively use the 3 different types of the headrest depending on the patient posture. So, but we had some issues with the Q-fix immobilization at the first stage. The first thing was a skin burn issue on patient's skin. Since the mask is thicker than the traditional one, if you use the water bath type, and the mask has kept a longer heat than before. So we changed it to the oven type to get rid of the infection problem as well. And we'd like to make it safer for the patients. And we have never seen this issue again so far. The next one is the Q-fix mask shrinking issues. Although this possibility is very, very low in short-term SRS treatments, but the mask may be deformed by the temperature or humidity and etc., which can use the difficulty in fixing the patient, as you can see in this video. So from my experience, also because it is made of the hardened material, it cannot be held tightly against the patients. And patients with a tumor located on the backside also feel really uncomfortable, and the patient said that the pain was severe. So I think everyone has same perspective on this issue. Due to the overall limitations, the Q-fix team releases so that it can be fixed using the cushion type, and they received official approval from the variant a while ago. After replacing with the cushion type, the part of the fixing the patient was very improved, and also the patient felt much more comfortable than before. So I was worried about the material of the cushion for the SRS treatments, but when I've taken the CT scan measurement checking, and I could see that it had a density similar to the air as the -800s on average. So we changed all to the cushion type at the moment. So we would like to see its immobilization's material effect on fixed beam. When measured by considering only the reaction to the material in a fixed beam condition, the cushion type has the most influence on the buildup reasons. So the maximum depth was around the 2.5 cm at center for the cushion type. And anyway, the mask had a less buildup effect that the cushion, because there are relatively many parts that pass through due to the holes. So however, the cushion and mask seem to have the more influence than expected, but this part is greatly reduced in modulated beam actually. So we definitely import the encompass frame model to recognize that it is the HyperArc plan. So this is only the things that tells the Eclipse that this plane is the HyperArc, because it doesn't have any hardware HyperArc sensor on the frame at all. So from my personal experience, for the HyperArc workflows, the controlling, the step is the most time-consuming part, especially in high-resolution CT. So as I said, we are scanned with a 1 millimeter CT scan, and some centers less than 1 millimeter. So it's very time-consuming part in HyperArc planning. So when we started the first time, we spent a lot of time on contouring for the body outline and normal organs. But now we found out the efficient way to drawing the body very easily, and also with this condition, and also the AI software helped us for drawing the normal organs automatically. So it really, really reduced our workload at the moment. So, for contouring parts, our physicians control all the small targets separately. Even though, it is too close like this, it is always better to separate them to achieve the effect of the dose photo for each target. So every time we drawing, the separately, even though we have the 30 targets at the same time. So before planning, we check whether the patient is safe through the virtual patient dry run and patient protection zone in Eclipse. And in HyperArc, that is the new trajectory before we go into the optimization, and we can select which target to treat and put different prescription doses. Based on selected targets, Eclipse provide a very spatially efficient isocenter by itself. So I'm pretty sure that you all may know about the new powerful algorithm inside the HyperArc. So, but let me explain each algorithm in more details. Actually, the first algorithm is the collimator angle optimizer, or we call it just as CAO algorithms. So the CAO algorithm is a key option to avoid island blocking between the targets. On the right side of these figures explain how the optimizer works before and after CAO. The use of the optimal collimator angle disconnected 50% or sometimes at 30% isodose line very effectively for the multiple match case. So here are the publications for the island blocking problem in multi-match case with the Rapidoc. So when you generate an SRS plan, the plan is spend time to find the optimal collimator angle manually to get avoided this problem. So of course, this process will improve the conformity significantly. So, but the HyperArc already has been included, CAO algorithm into the Eclipse for your convenience. It can be actually improve the workflow and also, it's very efficiency and it gives us the very nice quality of the plans. And also we can reduce the bridging doses between the targets, and also we can get a steep dose gradients close to target as well. And we can perceive simpler MSE motions as well. Okay, the next algorithm is the ALDO. So we call actually the automatic lower dose objective, and we call it simply less like, ALDO algorithms. So actually this algorithm allowed us to have kind of individually push doses to the respectively prescriptionized dose without having to worry about the multiple normalization point or values. So it is pretty sure that's the 98% or more all targets with the lower goals, actually. So if you get into the HyperArc optimization window like this, you can see this button on the top. And if you hit these buttons, it will apply it automatically. And this is comparison clinical data for the testing the ALDO algorithms. And just take a final look quickly. This size of the distributions for these patients. You can see how compact those distributions in using the ALDO way. So we see that dose bridging is decreased, and it is very clearly show the big differences between these two plans. For the conformity index value showed not that much differences between these two different plans. But as all you guys know, the CGI have a steep gradients, and if the value is close to the 100. But if you look at this number for using the ALDO value here, the value is almost reach out to 100, which means that it has a really steep gradient around the targets. So the final algorithm is the selective radiosurgery NTO, which is called the SRS NTO. This actually, we have this SRS NTO, which really benefits and helping is achieved these compact dose distributions we are seeing now, and really minimize those bridging between the targets. So a new normal tissue objective SRS NTO is automatically set for the HyperArc plans if you go into the HyperArc optimization window. And also the SRS NTO control the dose fall-off and dose bridging between the targets very effectively. So these features have been dramatically improved so that we can perform the VMAT-based SRS treatments. So HyperArc is different from the traditional Linux-based SRS program. So we have to decide how to do the plan conformation and the dose prescriptions. After we discussed with this issue with our physicians, we decided to apply the neurosurgeon's way, which can approach the max around the 130 to 150%. But the prescription lab decided to apply the method using radiation oncology, for example, 97% or 100% to targets. So after we get a plan confirmed by the physician, we do the patient DQA, but I will discuss this part in more detail later on. Okay. Oh, actually, we have 30 minutes of a QA slot on the day of the treatments. And during that time, so we are checking for the waist loads test and 60 couch QA in that time, but I will also talk about in details later in QA part. So when we do the patient dry runs, actually we are only using the patient mask with isocenter to reduce total treatment time. So we do not set up the patients and we do not running any patient dry runs get-togethers. So for the treatments, we treat the semi-automation mode, which check with the MV image during the treatments at each of the couch angles. Okay, based on our prescription dose in our centers, we usually complete all the treatments within the 8 to 15 minutes, actually the less than 10 minutes. But if the patient setup error is shown in MV image at each of non-coplanar couch angles, we take the combi CT again back to couch 0 and do realignments based on the 3D images. We do not change any patient setup or position based on 2D images. Basically, we use all the time, we use the 3D images as always. All right, so we would like to see the performance of the HyperArc new algorithms. So we compare it to RapidArc to see how much improved to the HyperArc techniques. So just let me talk about the one thing before we go into comparison data. So because of the insurance system in Korea, the SRS prescriptions can be treated with only 10 targets or fewer targets only. So if the lesion is over the 6, the treatment will be treated with a HyperArc technique, but the patient will be prescribed as FSRT prescriptions with 4, 6 fractions, things like that. And this case is a patient who prescribed a 20 gray with a 1 fraction for 3 multiple targets. And when we compare it with the RapidArc techniques, we found that the bridging dose between the targets decreased by the 15 and 25% each respectively. And for normal brain dose, it was too small, so the V12 evaluation was the meaningless for this case. So when I just look at it, the V2 or V3 doses, and it was found that about the 2 or 3 times the dose was less at the HyperArc technique. And as you can see this from this picture, there are 4 different sized tumors located on the same levels. So I also compared this case with the RapidArc plan to describe how efficient HyperArc it is. So looking at 20 gray volumes here, there's no actually difference between the 2 techniques, but the volume at 10 gray is nearly 3 times the differences. And those profiles show that the HyperArc technique case has obviously steep dose gradient, and also that those distributions between the tumors can also be really saved. So this is the super challenging case with 30 lesions at the same time. So actually this patient was already receiving the GammaKnife surgery several times in the past. So this patient was very young male patient, is about the early of 20s, and who had rejected whole brain RT at the times. Fortunately, we had installed the HyperArc and have been treating the 30 regions instead of the whole brain RT. So you can see how compact those distributions are really be able to get a fewer for work HyperArc doing itself compared to RapidArc. Even in areas for these targets very closely together. So white color is 30% that we are actually looking at here. That we see that dose bridging is significantly decreased between the HyperArc and RapidArc plans. So in fact, many people have been curious about how HyperArc can go in potentially replacing the GammaKnife for the treatments. And since our hospital has been treating the SRS patient with the GammaKnife surgery, so we compare with the GammaKnife to see if the HyperArc really has a reasonable result in SRS treatments. So the 7 patients with a range of the 3 to 8 metastases each were included in this test. And the target volume and the prescribed dose are detailed in this table. We classified it into the 3 groups and evaluated them to check the impact on target size. So this figure presented an isodose distribution for representative case of the group, and in 3 axial plans across the extension of the metastasis for the two techniques under investigations. So columns from the left to the right are GammaKnife and the HyperArc respectively, according to the target size group. So the dose prescription for this case were 27 gray, and the isodose line range showed from the 105% to 10% respectively, relatively. From the quantitative perspective, the illustration demonstrates the difference in terms of the gradients and the dose bridging mitigation among the various target size group between the GammaKnife and HyperArc. So these figures show the both types of conformity incidence and gradient index across all 2 SRS plans grouped according to the target size. It is shown that for all groups, the GammaKnife and the HyperArc plans performed similarly well across both conformity incidence. However, the gradient index, the results show that the GammaKnife is superior in small target size group, but above this gradient is very similar both techniques with a medium and large target size group. So when comparing the low dose of the normal brain between the 2 SRS techniques, the GammaKnife and HyperArc, it was observed not many differences significantly at each of doses. Therefore, we can see that the HyperArc is compatible with the GammaKnife in terms of the low dose spread into the brain. And when looking at the entire target size, so overall, not many differences between the SRS technique were observed between HyperArc and GammaKnife. And the large range observed in the max brain stem for the GammaKnife planning is measured in target location with using the fixed source geometry. So, and it was not able to optimize when it came to sparing OERs like in HyperArc optimization function. So the beam on time listed in this table were extracted from the 3 years decade GammaKnife treatment plans and recorded the HyperArc delivery time, which is the beam on time per fields, with a dose rate of the 1,400 with the 6 triple energies. As we can expect, the GammaKnife plans took 8 to 28 times longer to deliver than a HyperArc plan according to the target size and prescription dose and etc. So there's actually the limitation of the GammaKnife, to be honest. So we cannot actually use the dose constraint for the target and normal organs, and we can't actually control the Dmax, but we can still control the Dmax point in HyperArc optimization process. And GammaKnife can increase the delivery time exponentially, especially when the source decays. So if you think about the patient's QOL, quality of life, and the side effects, a HyperArc can be approached with a little freedom in treating the SRS treatments. So now I'm going to talk about the QA for the HyperArc. QA can be divided into the 2 parts, and the mechanical and the patient's the QA. So when checked some items through the MPC and PDIP provided by the Varian company, but we are also doing the additional QA solutions for accurate management. So we are checking the Winslow's test on the HyperArc treatment day, and we are using the stick type of phantoms that can adjust the 3 axes to get together. And we are checking the eye center position through the total of the 16 and sometimes 12 angles. And it has managed at 0.3 millimeter on average so far. We are really satisfied to use the RIT analysis software because this program is very helpful in identifying the current location of the laser and the condition of the mechanical error of the equipments, because it informs the deviation error at each of location and also estimated, actual isocenter, things like that. Therefore, the when the result exceed the tolerance, so like 0.5 millimeter, we can determine the causes a little faster. So since we are all using the image-guided radiation treatments, we relied on image quality and 60 couch movements a lot. So we need to check the 60 couch performance. We actually benchmark the commercial phantom and the generated 60 couch QA plate by the 3D printers. And the mechanical part is checked by the 2D inclinometer simply, and the phantom is used for the imaging QA. So for imaging QA, imaging-based QA, it is necessary to check whether it comes out as much as intended plate movement position through the imaging fusions. After applying the movement of the 60 couch based on this number here, and to check if the initial laser setup is matched with the phantom setup. So this is how we are doing the 60 couch imaging QA at the moment. Right. I'm going to talk about the HyperArc DQA in our departments. The variant provide the solution to achieve the rapid dose fall-off and the less bridging doses with the auto SRS NTO and CL algorithms supported in HyperArc planning system. However, while the planning and treatment of the HyperArc are very concisely automated, but there is no guidance to implement this metric quality assurance to verify the beam characteristics of the HyperArc delivery for the SRS treatments. So we do the measurements and evaluation for target dose fall-off and bridging doses in the various simulation close to the SRS brain mat case. So in this test, as a first step, we compared the use of the SRS NTO function to see how much improvements the SRS NTO has made in gradients. So this result show that the dose gradient close to target has improved about the 30% using the SRS NTO option. So this is conventional COM-based SRS gradient guideline. It is normally showed the 3.3 in D90 to 45. And if you use the HyperArc SRS NTO options, the gradients showed in 4.39 millimeter and the 6.13 millimeter if not used. So the HyperArc new SRS NTO algorithm improved the gradients by the 30 to, let's say, the 40% already. The traditional SRS QA method is introduced, but if the patient is heavily loaded, like in our institutions, we thought about which one is the most efficient and suitable for the SRS in our clinic. So we tested all the equipment what we had before, and we really wanted to evaluate in the same environment as possible the HyperArc treatments. So we have now settled down using the PDIP and the SRS map check system. So some of the studies actually pointed out that the QA method based on using the 3D panel constructed with the 3D printer provides a better end-to-end test than traditional the patient quality control test because it really matches with the clinical patient workflow. So as first step, we designed a phantom to measure the multiple tumors in various areas considering in real HyperArc patient cases. So to evaluate the dose gradients in delivered dose distribution, especially for the SRS treatments, it is significant to obtain and to make sure the reliable and the precise and calibrates the curves for the film dosimetries. However, the dosimetry using the GAF chromic film are affected by the scanning parameters such as the contrast, brightness, and highlight. So we investigated the impact of the range of the optimal densities and the slope of the calibration curves in terms of those on evaluating delivered dose distributions. As we adjusted brightness from the 0 to 20 and the contrast and highlight from the 0 to 50, we obtained a very different calibration curve depending on the scanning conditions and color channels as shown in this plot. So we focused on the effect of the calibration curve of the red and green channel at this condition and compare to the conventional calibration curve taken at a typical scanning using the Epson scan software. So to evaluate whether those gradients and bridging doses between the targets, we selected two different cases here. This test compromised in the two different cases. One is a single target case to see the dose gradients, and the other one was the selected multiple METs case to evaluate the bridging dose by the MSE movements and optimized segments using the CAO algorithms. So these two plans are using the 6FFF and they already got a GammaKnife surgery several times. So that's why we prescribed the 6 and 8 grade for each of plans. So the single target field measurement results shown here, we bring all that into the analysis software in-house software. You can see the film results here that the brightness 20 and contrast and height left 50, the plot, and conventionally, the 7 gray and 150 centigrade have the level of the 15% of the matched bridging doses. But the level is very small differences, so it still look like, very reliable between two plots. So the multi-target field measurement results is shown here. The multi-target contains many complex variables, and including the MLC error, which can affect bridging doses and gradients a lot. So the result of this case are particularly differed a lot of depending on the OD curves and condition. But we selected one of the best condition and to apply that. And the actual field measurements were more closely matched with the log5 based result involving the various mechanical variables. So original plan showed the significant under predict the dose measurement which not contains MLC complexities. And this is the result of measuring the SRS map check that we are actively applying now. And this device is actually dedicated for the SRS and SBRT, so it has very high resolution to the array detectors. Don't forget it. This one is not just like map check system. This is called the SRS map check system. Some people really confuse between the SRS map check and map check system. So this machine is highly dedicated for the SRS and SBRT treatments. So it can be actually measured in the most similar environment to the HyperArc, can be checked in real time, and also can be measured in a desired slice for multiple targets because it becomes a phantom rotation component. So this is a very straightforward process with many ways to perform the HyperArc QA. So in the case of the single reasons, we usually measure in its eye center and measure in non-coupler like the HyperArc real treatments. And the most of single target case passed at 99 to 100 without failure when we are doing the 2 mm/% gamma evaluations. So here a more complicated case, the multiple measurements results shown here, when we treat the multiple METs, we sometimes treat the 2 or 3 at the same time, but we often treat nearly, sometimes the 10 at the same time. So in that case, we decided to measure the smallest target and largest target, but we basically, measured more than 3 points at the same time. So SRS map check have the flexibility to display the analysis in multiple planes at the multiple angles, so we can rotate it in a stereo-fan angle as much as possible. But there are tons of the advantages using the SRS map check, but it also has some limitations. We prefer to make measurements in the same embodiment as a HyperArc. So we measure it with a non-coupling angle, but when we move the targets we want and try to measure it, we need to check the guide and the proceed because there may be the collision between the couch and gantry, which means the phantom and gantries. So if you measure it with a non-coupling angle, there is possibility of the damage due to the radiation exposure to the radiation map, SRS map check, the electronic part. Therefore, when measuring the multiple targets, and there is a limitation to the measurable range. So if the center is the possible SRS map check is the low dose area, and also without the target parts, then the accuracy of the results, getting really worse from my experience. So since the most of the QA results were pretty good, we really wondered if it was the really accurate when HyperArc was delivered from the machine side. So I tried to dig in the log files. So the log files are automatically generated by the machine after treatment. So this log file consists of the whole bunch of data information, such as the gantry angle and jaw, MLC, carriage differences, delivered MU values, and things like that. So I analyze HyperArc's delivered patient log files. So when we analyzed the representative case, we found that very surprisingly, the machine was working very accurately on every single point. For example, if you look at the gantry and the carriage angle here, the maximum error is less than the 0.01. That's why we could see that result through the QA devices. It was really good, and every time it's passed. And the delivered dose is very well in all agreements with the planned dose. So when we can actually have a look at these examples cases here, and it shows that the position error of the HMLC leaf an individual control point. It may cause some dosimetric error in the film measurements or your QA result as well. So although the dose delivery is continuous and the MU delivered in total during the treatment is the same as the planned MU, the MU delivery for each segment can be very, very different. So while the difference of the MU per each segment and the per each arc is very, very little, the estimated dose distribution using the actual delivered MU is discretized. Those calculation can be different in SRS using the WMAT. So as you can see this figure, for single and multiple SRS treatments, when we analyze the MU differences per segment, we found that the number of segments where a little bit higher MU was delivered is larger than the other where less MU was delivered. So this is the example cases demonstrated. You can see this figure is under predict dose delivered significant for these targets. On one of the illustrated is that when using the log file information into the dose calculation system directly, you can see that the bridging dose has increased that refer to the MLC error of some of the reasons. So the dose simulation using the log file was really useful to estimate accurate dose delivery. So actually, what has been changed compared to the traditional SRS treatments? For physicians, actually, they don't really actually check the patient setup error with the MV image at the non-coupling couch angle during the treatments. So based on these data, they can assume that their margin very well. And also, they can put different prescription doses are possible, and efficiency is very increased with the single eye centers. And prescription dose can be escalated because the CR is very well controlled by the optimization, and we can reduce the OAR doses a lot. But for planners, they don't really need to counter extra shooter target anymore for getting a steep dose high gradients. And we can actually decrease the countering burden a lot. And also we can treat this is the non-coupling technique, so using the fixed geometry by the HyperArc and a lot of the good algorithms such as the CAO, SRS, NTO, that all those is supporting to getting a high quality plan and even the less experienced planner as well. And also in treatments of the multiple metastasis with single eye centers. So we don't really need to consider geometry for each individual targets at all. And also the GPU system can be supported with fast calculation speed. So even though we applied an accuracy and the WMAT technique for such a very complicated cases, GPU can solve and resolve, the fast calculation speed. For radiation therapists here, they can also reduce the setup time, and because they can only use the in-canvas frame and the Q-fix mask, they don't really need to attach additional cone and etc. The MLCs, they don't need at all. And also they don't need to change the target isocenters when multiple targets we are treating at the time. And also, once they click the buttons, that everything on all of treatments will be go through automatically, so they don't really need to think about every buttons, every steps. So it's very convenient. For the medical physicists, we still need to think a lot of things, to covering the SRS programs, because, actually, we can say that reduced and simplified data center checking the patient setup can be confirmed in advance during the patient dry run in an Eclipse. And also, we don't need the additional beam commissioning for the SRS con, the beam data. And also, we don't need any, the check and etc., the stabilizers for the patient setup, the frame or couch to stabilize, etc. But we still need to manage of the 60 couch and imaging and small field beam data and those the DLG factor and transmission factors, things like that. And also the patient DQI is still time consuming with the film. If you guys are using the film or the point does by the ion chamber. So let me recap for the HyperArc technique as summaries. It is very clear that the HyperArc is good technique, and the plan and treatment has become very concise compared to the traditional SRS techniques because they can have a really good workflow and simplifies. And also we can put the SRS the schedule in a similar time slot as conventional radiotherapy. And also, we can always get a higher quality of plan, even though we know the less experienced planners handled by this plan. And we can utilize the modern Linux, for example, the Edge or TrueBeam. They can also deliver the the SBRT and IMRT of VMAT of 3D. And it enables treatments of the multiple metastases with a single eye centers at the same time as always. And we can reduce the dose to the surrounding normal brain dose and also who the patient who are being retreated. So with such good techniques, what should we think about and improve? Although the system has been automated, we still have to simplify the time to prepare for SRS treatments compared to the past, but it still takes some time for the physicists. The protocols must be organized to fit in reality of the each institutions. And the controlling burden is still really severe in HyperArc, so it might be reduced, in heavy readings. It can be really, it can be the really heavy reading in your departments. And even though, the current mask type has become the very simple setups, but there are still some parts are the wrecking the situation. So we hope that mask length and tongue bite will be improved so that we can, the patient can fix a little bit better than now. For the QA part, many institutions have transitioned to the film to the PDIP due to the time constraint, but it is hard to check the target gradient and fluence exactly. So it needs to use additional device for the multiple match case actually. If the QA is failed, it is really difficult to know the cause of the tracking the problem very easily. So I think it will be more helpful if the Mobius or log file based information provided detailed, detailed in real situation from the machine side. So as I speak right now, I believe that the HyperArc towards the high precision radiosurgery for brain metastases at the moment, but unfortunately, the physicists still need to think and care a lot of the stuff for the QA, but we need to compromise to reduce the process as much as possible. So I need to thank all the AJU HyperArc project teams who are very actively contribute on this study, and also not to mention in particular my colleague, Professor Jian Park, who provided some slides. So I'd like to thank everyone for taking the time to listen to this presentation. It's been a really pleasure to share our experience and insight with you today. As we continue to push the boundaries of the radiotherapy, I'm really excited about the future and the potential to improve the patient care even further. So if you guys have any questions or would like to discuss any topics further, please feel free to reach out to me. I will look forward to hearing your thoughts and insights. And thank you once again for your attention and participation. Thank you.
Thank you, Professor Mack. Thank you for your in-depth explanation for every aspect of the HyperArc. It's sorry for the limited time. And for the audience, please leave questions before you forget on the chat window. So we are going to move to the next talk on the CyberKnife. About CyberKnife, will be given by Professor Hojin Kim. Professor Kim finished his PhD at Stanford University in 2014 after working as postdoc researcher for a while, and he came back to Korea 2017, and now he is working at the Department of Radiation Oncology, Yonsei University as assistant professor. He's working actively and now principal investigator for grants and published 18 SCI papers. So please welcome Professor Hojin Park.
Okay,
So could you
thank you for a
start
nice
your talk?
introduction.
Yeah.
Can you hear me? Okay, yeah.
Yes.
Yeah. Thank you for a nice introduction. Hello, everyone. Can you see my slide, right? In the full screen, no?
Yeah, I can see your full screen.
Right, great, okay. Okay, thank you for a nice introduction. Hello, everyone. Thank you for inviting me to AFOMP webinar this year. It is such a great, it is such an honor and a pleasure to me. I hope what I'm going to speak about brain radiosurgery using robotic MRT-7 will be beneficial for your clinical work and research. Before starting, I'm going to briefly introduce our institution. Severance Hospital is the university hospital founded in 1885 as the first Western Star hospital in Korea. And Yonsei Cancer Center was established in 1969 to be specialized in cancer treatment. Now, Yonsei Cancer Center is operating 13 linear accelerator consisting of 8 conventional linear accelerator manufactured by Elekta, 4 tumor therapy, and a single robotic MRT, both from Accurate. And robotic MRT is a main theme of this presentation. Also, we are operating carbon ion radiotherapy facility, which is the first heavy ion radiation therapy center in Korea, and the only institution having multiple gantry units in the world. We are commissioning the second gantry unit at this point. Radiation oncology at Yonsei Cancer Center treated about 8,000 patients last year, in which brain cases took about 10% among these. The number of patients treated using robotic MRT has been fluctuated a little bit, has been slightly decreasing in recent 2 years due to software upgrade in 2022 and machine decommissioning because of the Linac head replacement last year. On average, for sure, we are treating 300 to 400 patients every year using robotic MRT. From now on, I'm going to take a closer look at some features of robotic MRT. Just in case you are confused, I'll let you know in advance that I'll use the terms CyberKnife and robotic MRT interchangeably. The objective of the treatment planning for radiotherapy is to maximize the dose to the target volume while sparing the dose to the normal critical structure simply. Recent evolutions in radiotherapy from advent of MSC to a 3D image-based treatment to intensity modulated radiotherapy have been aiming to achieve those objectives. However, meeting the two objectives simultaneously can be challenging with the conventional coplanar treatment scheme as illustrated here, where the surrounding normal critical structures may obstruct the target volume from receiving high dose of radiation. In such condition, non-coplanar treatment scheme can maximize the dose to the target volume by avoiding the critical structures in their beam path. Also, non-isocentric beam arrangements can provide greater degree of freedom for target volume coverage, so possibly further improving the plan quality. So these non-coplanar and non-isocentric configurations clearly represent and symbolize the CyberKnife, which was enabled by a moving robotic arm named Fuka, as shown in this figure. Additionally, real-time tracking and couch adjustment capabilities can enhance the security and safety of radiation therapy. These features made it possible for conducting stereotactic body radiotherapy and radiosurgery using CyberKnife. It is important to be aware that CyberKnife is differentiated in several aspects from some conventional radiosurgery units, which are primarily focused on the brain radiosurgery. First, this doesn't require invasive immobilization for patient setup and tracking. Also, it provides different tracking strategies to various body sites, enabling treatments for nearly all body regions, including the brain. To better understand the characteristics of robotic MRT, the following image shows its principal components. Linear accelerator was placed at the end of the robotic arm, named KUKA, as I told you. Kilovoltage KV X-ray source detector synchrony camera are required for motion tracking and image guidance. Also, CyberKnife can offer a 6-axis couch. However, we are currently using 5-axis couch. Cancer Cancer Center is the first institution in Korea that installed the CyberKnife M6 named Robotic MRT featuring MSG Kim. Sorry. The table in this slide compare robotic MRT against the conventional linear accelerator and tumor therapy. As seen in the red box, CyberKnife has unique image guidance system. Conventional LINAC provides volumetric X-ray convolution images usually, but robotic MRT doesn't. Instead, it offers 2D KV X-ray images acquired at plus/minus 45-degree angles, which are supposed to be compared against the 2DR images produced from the planning CT images for image guidance. This seems to be problematic with respect to the accuracy of image guidance, but the simpler the better and more powerful, especially when it comes to the real-time motion tracking. The following shows why. With volumetric images, the number of imaging sessions is constrained to be 1 or 2 because of the time elapse or the radiation exposure to the patient. Contrarily, the 2D KV X-ray images are free from those concerns and can be performed repeatedly for tracking patient motion with user-defined time interval, as described in this figure. The beauty of CyberKnife is its capability to provide various motion tracking strategies to different body sites using 2D KV X-ray images as illustrated in this slide. Especially the fiducial tracking is the most frequently used protocol for treating prostate, lung, liver, etc., although it requires for 3 to 5 fiducial marker implants around the target body. For brain radiosurgery, skull tracking is used in most cases, working as follows. User can define the align center during the treatment planning, which was recognized in the process of DRI image generation. Tracking is performed by comparing and matching the skull placement in DRI and KV X-ray images. You can see the following images displayed in the treatment console as an example, which produce the offset values, indicating how much the couch needs to be translated and rotated. The fiducial tracking can be more powerful when it is combined with a so-called synchrony camera that is supposed to keep tracking the external markers on the patient. This is known as synchrony tracking, the most representative tracking protocol of CyberKnife. This system generates a model by analyzing the correlation between the movement of the external diode markers captured by the synchrony camera and internal motion obtained from the KV X-ray images. Next, CyberKnife shows a unique beam generation structure resulting in different specifications. Unlike conventional LINAC, CyberKnife doesn't have enough space in the beam generation structure, as its linear accelerator is placed at the end of the moving robot. This factor removed the placement of the flattening filter following the tungsten target and inevitably shortened the SAD to 80 centimeter, which is usually 100 centimeter. This must be good for the dose rate. So CyberKnife has a dose rate of 1000 MU per minute that is greater than the other magnetron-based linear accelerators, while sacrificing the percent depth dose, PDD. This is kind of simple physics. The shorter SAD, the lower PDD due to the inverse square law. Robotic MRT has different types of collimators by exchanging the part of secondary collimator. The fixed cone is a conventional type of collimator or CyberKnife with 12 different sizes. The biggest cone size is 60 millimeter, which is the machine-specific reference field of CyberKnife for output calibration and output factor measurements. Since exchanging the fixed cones must be performed manually, it is important to be identify the cone size before the treatment and the QA test for safety. Iris collimator was developed to address the limitations of the fixed cones by permitting variable collimator sizes without usual interventions, but iris was not widely adopted due to additional commissioning process, which is time-consuming relative to the benefits. CyberKnife M6 finally incorporated MSC into the system. Interestingly, as you can see here, the shape of MSC is slightly different from that of conventional linear accelerators. In fact, the leaves were intentionally tilted by 0.5 degree to reduce the interleaf leakage. The other interesting fact is that the initial M6 version was equipped with a 2.5 millimeter resolution leaves, which were replaced with the leaves having worse resolution, 3.85 millimeter due to some technical issues. In spite of that, what really matters is M6 release with MSC equipment made a huge contribution to reducing the treatment time of CyberKnife. Next, non-coplanar and non-isocentric features of CyberKnife will be specified. Workspace means a virtual spherical surface which can be generated relative to a certain reference point. As a matter of fact, although CyberKnife is a non-coplanar treatment unit, it's not true that all spots within the workspace are available for the treatment. Only specific points defined as nodes are supposed to be assigned around the reference point. Also, it is important to be aware that each node on the workspace allows for a maximum of 12 non-isocentric directions, which is not infinite number. Thus, the key issue to discuss here is how to define the reference point, determining the workspace and node. To remind, the nodes are located within the workspace as mentioned earlier. A new concept path is defined as some designated route connecting these nodes. So a calibration of the path is required in the process of annual queuing to make sure that the central path is exactly pointing to a reference point known as isocrystal. That is the tip of isopost, physical isopost, as illustrated here. Then we need to see if the path calibration was accurately conducted. The first step is called A-queuing, which is similar to Winston nuts that identifies the coincidence between radiation and mechanical isocenter. And the purpose of A-QA is to ensure the accuracy of radiation isocenter after path calibration. It delivers radiation to a cubic phantom having a metal ball inside at two different robotic arm angular positions, 0 and 90 degrees in a coplanar setting. And the difference between two isocenters was computed, which needs to be a sub-millimeter accuracy, as seen in the following. We can make it more realistic by E2E end-to-end test. This is designed to be simulating actual treatment scheme with different types of phantoms or various motion tracking scenarios, as shown here. These phantoms are scanned at CT simulator, then being imported to the TPS board controlling and the treatment planning. The resulting plans are delivered in the treatment console like actual patient treatment. And those distributions are evaluated using the film dosimetry. Thus far, I have been focusing on the QAs for hardware, but I'll move on to the treatment planning system, which was recently upgraded in our institution. The upgrade was made in 2022, which took about 5 weeks, including firmware and software upgrade, followed by additional QA process, including annual path calibration and E2E tests, and some part of beam commissioning for the new dose calculation algorithm. We've got numerous benefits from the upgrade in terms of dose calculation algorithm, plan optimization, and some additional functionalities. Basically, the precision TPS upgrade made every task faster. It is a little bit nonsense that the older version TPS was not able to do the multitasking, although the name of the system was multiply. But the new system precision can do the multitasking, fortunately. After the upgrade, robotic MRT and Radiosurgery tomotherapy share the same IDMS software, which mainly controls the precision treatment planning system. The following table shows all those calculation algorithms available for the fixed cones and MS collimators. The most significant change in precision TPS was that the Monte Carlo dose calculation algorithm became adaptive to MS collimator, in addition to the fixed cone and the iris collimators. It is important to note that the pencil beam algorithm, FSPB, is available for the MSC collimator, but there is no convolution superposition algorithm provided, unfortunately. Bolo optimizer provided by Precision TPS Neuralink enables for IMRT-like treatment planning for the MS-based plans, performing the full map optimization first, followed by lift sequencing algorithm to select actual segments for the dose delivery. Also, it offers additional constraint to the plan optimization. Both constraints of full map smoothing and total amnio reductions are closely associated with the treatment time efficiency. But we may have to take care of a balance between the plan quality and the treatment time efficiency when trying to use these functions in clinic. Beam data required for the precision and multi-plane TPS beam modeling include output vectors, profile shape, and TPR data similar to the other TPS, but beam data acquisition may take a little more time as the beam modeling is based on the TPR data rather than PDD. So for your convenience, we recommend acquiring the PDD data in the part of the beam data commissioning so that it can be used for the periodic QAs afterwards instead of TPR. Next, I would like to look into some brain SRS treatment plans using robotic IMRT at Yonsei Cancer Center. We are treating several body sites using robotic IMRT as seen in this figure. According to our annual statistics, 319 cases were treated using CyberKnife for about 1 year, in which the partial breast irradiation cases took the biggest proportion. Brain SRS cases occupied about 7%, entirely 23 cases. Following table presents specific information about the brain SRS cases. The brain SRS patients were treated under consistent specification, which commonly included a square image tracking method, fixed con collimator, Monte Carlo dose calculation algorithm, and a single fraction regimen. The remaining parameters were slightly fluctuated as illustrated in the following slide. Prescription dose ranged from 18 to 24 gray, with an average of about 19 gray. The maximum dose relative to the prescription dose was approximately 160% on average, indicating that the resulting plans had very inhomogeneous dose distributions inside the target volume, which is beneficial for achieving the step dose fork gradient outside the PTV. Average PTV size was 1.3 cc, which means very small volume being treated. Thus, the con size had to be that small, averaging around the 10 millimeter. The average dose delivery time was 27 minutes with a mean MU monitor unit of 7,000. Some people may wonder why fixed cons are commonly used for treating brain SRS using robotic IMRT. The key reason is associated with the smallest field size available for the collimator. Namely, fixed con is able to have a smaller field size than MS collimator. Another reason is related to the preference of radiation oncologists. 3 radiation oncologists in our department are treating brain SRS with robotic IMRT. Before the software upgrade, Monte Carlo dose calculation algorithm was available for the fixed cons only. Thus, they are used to adopting the fixed cons for treating the brain SRS. But importantly, for the other body sites, the use of MSC is predominant in our institution. So I would like to share a typical brain SRS case, which has PTV of 1.3 cc with prescription dose of 20 gray. Monte Carlo dose calculation algorithm was used, and 10 millimeter fixed con was selected for the treatment planning. The plan was optimized to ensure a PTV dose coverage of 95%, where the maximum dose was 170% of the prescription dose. So this is also a very inhomogeneous plan. MU was about 9,000, leading to a dose delivery time over half hour. As seen in this planning results, the dose conformity to the target volume was fairly good, and the dose to the critical structures was well spared. As you can see here, the maximum dose to the hippocampus and brainstem was about 2 gray, which is only 10% of the prescription dose. Finally, I'm going to wrap up my presentation by talking about some important considerations of robotic IMRT. First issue is about patient-specific QA. AAPM TG report 135 emphasized the need for patient-specific QA. In fact, most CyberKnife plans are non-isocentric, but there's no periodic QA task to ensure the accuracy of non-isocentric plans. Even E2E tests are not sufficient for this issue. Thus, TG reports that patient-specific QA is the only way for guaranteeing the accuracy of non-isocentric plans. Thus, it is recommended to perform the DQA process as a part of commissioning or monthly QA and list. At Yonsei Cancer Center for your reference, we've been conducting the patient-specific QAs for all treatment for all treatment cases, regardless of the type of collimators used. For all body sites except brain SRS, 2D array detector Octavius from PDW has been employed for the patient-specific QA. Interestingly, we made a single plate embedded with a single couple of metal balls inside, which was placed at the top of the phantom in order to facilitate the fiduciary tracking in the QA process. Unfortunately, however, we couldn't use the 2D array detector for brain SRS cases because of the potential collision with the moving robot. Thus, a small size phantom named stereotactic dose verification phantom was adopted along with the A16 ion chamber for absolute dosimetry and film dosimetry for relative dosimetry. As the PTV target volume is pretty small, measurements need to be performed twice in most cases for absolute and relative dosimetry respectively. Thus, we are looking for some alternative to complete all process in a single measurement for the brain SRS QA. The second issue is about dose calculation algorithm. On IRC website provided by MD Anderson, you may find some information about the dose calculation algorithms approved for the heterogeneity correction. As seen in the following, for CyberKnife, only Monte Carlo dose calculation algorithm was approved for the heterogeneity correction, unfortunately. This means that the other calculation algorithm, ray tracing for the fixed cone and FSPB pencil algorithm for MLC, may not be appropriate for the lung treatment potentially. Our institution published an article regarding this issue about 6 years ago. The 8 lung MLC plans calculated with the pencil algorithm resulted in the significant differences between the measured and computed point dose values, which are bigger than 10% in all cases, which is a very serious problem. Therefore, the Monte Carlo dose calculation algorithm must be the first option for the treatment planning when the lung structures are involved in the treatment, such as lung and bone RT cases. The third issue is concerning the small field dosimetry. As mentioned earlier, our institution has been treating the brain SRS plans with very small field. To address this, we chose a 16 ion chamber for patient-specific QA having a collecting volume that is only 1% of the pharma type ion chamber, which is very small, but volume averaging effect may not be fully overcome even with this type of chamber. Additionally, this ion chamber is not identical to the detector used for the beam commissioning process in our institution, which was SRS diode chamber. So this may require for additional corrections for measurements. And there is a very informative publication that can clearly answer this complication published in PMB in 2017. They revealed the discrepancies across the different detectors in small field dosimetry of CyberKnife, as being demonstrated by both Monte Carlo and actual measurements. Interestingly, a 16 ion chamber was found to be kind of outlier, yielding the biggest difference compared to the other detectors, especially in very small field. This strongly recommends adjusting the output factors when we use a 16 ion chamber for patient-specific QA. In the beam commissioning process, we measure the output factors for both A16 and SRS diode chambers, which have been reflected in analyzing the results of patient-specific QA so far. So thus far, I've been looking into the features of CyberKnife characterized by its non-coplanar and non-isocentric configurations To guarantee its accuracy, annual path calibration must be performed, followed by a QA process for verification. It is important to remind that patient-specific QA is the only way to make sure the confidence of the non-isocentric treatment. Various motion tracking protocols for most body sites throughout 2D KV X-ray images are another fascinating point. TPS upgrade to a precision TPS is totally recommended so that Monte Carlo dose calculation algorithm can be used for the MS collimator. This is required for heterogeneity correction as mentioned earlier. Brain SRS using CyberKnife is performed with a very small field. Thus, we need to find proper strategies for accurate dosimetry. So this is the end of my presentation. Thank you for your attention and feel free to contact me if you have any questions. Thank you.
Thank you, Professor Kim. We save a lot of time, and thank you for the basic introduction. And I have a quick question. So I think one of the most strong points of CyberKnife is that tracking.
Yes.
So for the brain tumor, you normally use the skull tracking. And
Right. Yeah.
do you know how often the image is taken and adjust the position?
So it can be user defined. So normally we
Right.
took the images by 1 minute, 30 seconds, 1.5 minutes, or 2 minutes. It totally depends on the therapist. There is no
Okay.
critical, no regulations about that. So normally 1.5 minutes is our protocol.
And have you looked at the log file, treatment log file, how much the correction was applied during the treatment? Because that will be, I guess, at the end of the all talks, I would like to give you all the question about the monitoring during the treatment, and also maybe HyperArc, the Linux-based one, they have the 60 couch. So each system has some strong points. So
Right. Yeah.
for the CyberKnife, if you look at how much the motion is occurred during the treatment, then it will be very insightful to maybe it gives raise some warning sign to the system. So as the Professor Park mentioned, they want to implement the motion patient monitoring system during the treatments, like using the SGLT system. So yeah, I'm just wondering. So
Yeah, that's I think pretty interesting point that I couldn't come up with. So yeah, we can
okay.
as far as I'm concerning you, as you mentioned, we can look over the treatment history throughout the log file. So we can try it. Yeah.
Okay.
Yeah.
Okay, thank you, Professor Kim. So
Thank you.
we are gonna move to last speaker, Professor Andreas Mack. So Professor Mack is an expert in radiosurgery with a lifelong career dedicated to the field. So I found in his CV, he started with the Linux-based radiosurgery first. I think he also got the PhD relating to on this radiosurgery plan optimization or plan dose calculation. And after then, he experienced GammaKnife, CyberKnife, and over 8,700 patients already. And right now he's using the ZAP-X. He has been instrumental in establishing multiple radiosurgery centers across Europe, including pioneering the use of ZAP-X in Switzerland in 2019. And he also achieved many academic achievements, including as the professor Chung mentioned, he involved in the MR, the imaging accuracy protocols, and so right now he has held the leadership position in his own institute. So welcome the Professor Andreas Mack, and please, if you're ready, you can start your presentation.
I'd like to shortly give an introduction on radiosurgery and then focus on the ZAP-X technology. I think we have to keep in mind that radiosurgery is a borderline area between neurosurgery and radiation oncology. And we all use a spatial precise shaped irradiation to treat small, well-defined structures. And I think we have to distinguish between radiosurgery and the classical fractionated conventional therapy, because we do not allow any kind of repair in between the fractions. That means we have a higher biological effect. And this can, and most often leads to a better tumor control. But we also do a kind of portioning of the dose, but not in sense of according to time, but by using a variety of beams, in our case, GammaKnife and ZAP, several hundreds of beams. So we have a high tumor control, very little repair, and this is only possible by using extremely steep dose fall offs at the edges. So we all know that one of the pioneers who brought the complete topic to all of us is Lexell. And when he was in Karolinska, I know his son on a private basis, he told me that his father was suffering from the fact that back in the 50s, almost 40% of the patients died during open surgery. So he wanted to have a machine, a technology to deliver high single dose of radiation to a small, critically located intracranial volume through the intact skull. And if you look in terms of evolution, what happened, so in the 60s, everything started with ideas to use protons in the US. Then we had the first prototype invented by Lexell and Börje Larsson. Then we had the first GammaKnife installed at the Karolinska in '75. And then the idea to kind of use this methodology also with Linux, introduced by Betty Derinshinsky in the USA, and then by Beauvoir Gainesville with a floor stand, which we had actually in southern Germany, where I derive from. If we continue this historic line, then you all know about the GammaKnife types. The first CyberKnife introduced by John Adler in '99. You know, John Adler was a neurosurgeon who had a fellowship at Karolinska and was inspired by the idea, and he wanted to have this for the complete body. Then further developments of the GammaKnife, ideas to use tomotherapy, CyberKnife, the latest cover, and then ZAP-X. You have to know that ZAP-X was introduced or developed by Varian because John Adler was a consultant at Varian, and they discussed to have a intracranial dedicated device. And so the idea came up to develop a gyroscopic approach very close to the GammaKnife. And then finally, Waring decided to not follow this idea anymore. And John Adler bought out the idea and founded his own company, ZAP, meaning cut, and X for X-rays. So it's a kind of a surgical tool using X-rays. So I think we have to keep in mind that we have to distinguish between the limits of a methodology due to plain physics and the hardware, and what can be achieved by using sophisticated software. So if you look in terms of pure physics, there is an influence on the distance from the focus to the target. There is an influence on the source side, and there is an influence on the collimating system itself. And all these three factors have an effect on the so-called penumbra, which we all know. And the smaller the penumbra, the smaller the shadow, which you don't want to have, because this shadow will have an influence on healthy tissue, the better the potential which you have due to hardware. And this leads to the profiles, which we all know. And if you look on an overview on the machines on the market, all methodology has dramatically improved over the last years. But still, there are small differences. So if you look at Linac versions and adapted versions, you still have the distance of 100 centimeters from the source to the target. This has to be because otherwise you wouldn't be able to treat prostates, for example. Then CyberKnife as being the representative of a dedicated device to treat the whole body. And on the right dashed line, you see the dedicated devices for brain only, which would be the GammaKnife and the ZAP. And you see the distance from the source to the so-called unit center point is much smaller, 40 and 45 centimeters. So this does have an impact on the quality of the penumbra. It's very easy if you think about a flashlight and you go with a flashlight very close to the wall. The closer you go, the sharper the shadow is. Concerning the ZAP, remember the energy which they use is only 3 MV. And if you take into account that 3 MV would be the maximum energy, the most output receive at 1/3 of the maximum energy, which is roughly then 1 MV, and this is very close to cobalt. And this was done on purpose to be very close to the GammaKnife, and thus expecting very similar clinical results. So this is a direct comparison of the both intracranial technologies, and you see the different angles which you use for therapy. So the idea is to, if you look at the left side with the ZAP, to disallow any beams coming directly from the top or the bottom. So you do not allow any beams in craniocaudal direction, because you don't want to have any out-of-field dose inside the body. So this is the usual situation which we face in a daily situation. We have a tumor, we have a diagnostic uncertainty which we have to take into account. And if the tumor is moving, we have to give an additional safety seam. And this safety seam is proportional to the volume. If the volume is getting too big, we have to split up the dose. And we know from the daily routine, there are two mechanisms. You can split up the dose in a conventional fractionation sense, or you can split it up into geometric portions, several hundreds of beams. And this leads us to the cornerstones of radiosurgery. The tumors have to be rather small, clearly distinguished in imaging. You need controlled patient positioning, and you need a technique using steep dose fall-off. And If you now look at the similarity between a GammaKnife and the ZAP, you see on the left-hand side the sectors and all the beams intersecting at the unit center point. And on the right-hand side, you see the gyroscopic approach. That means you have two hemispheres, two shells moving within each other. And the inner shell is tilted by 45 degrees. So you have numerous of angles where you can hit the unit center point. And this would be the situation at our institute. The machine has been brought in through the ceiling, and you need no bunker bits between the machines, totally self-shielding. You see the red line on the bottom, and that means out of this red line, you will receive less than 1 millisievert a year. So accompanying patients can stay outside the red line during treatment. So that would be the system in a side. You see that everything is attached to a so-called gantry, a ring. You see the imaging system, which is mounted inside the inner sphere. So it's an X-ray system which controls via live images and compares these live images to the pre-taken CTs, the DRRs. And if there is any deviation, the table will correct for this. Then we have the small standing wave LINAC having a collimator wheel in front out of tungsten with a diameter of 16 centimeters. And if you keep in mind that the distance from the source to the unit center point is only 45 centimeters, already 1/3 of the distance is guided by a conically drilled hole in this collimator. We have a real-time dose monitoring system. That means the dose after being penetrated through the patient is being measured and being compared to dose calculation prior to treatment. So this is a collimator wheel, which you see. It's, as I said, 16 centimeters of tungsten. It has 8 holes, 8 diameters between 4 and 25 millimeters. They're conically drilled. There's one plug position. That means there's one position where you disallow a beam to go through. And as I said, it's conically drilled. So if you look from a theoretic consideration about the potential positions, there are 16,000 combinations, because you have an inner sphere where you can stop every 6 degrees, leaving 60 positions. And you have this for both spheres. So it's 60 multiplied by 60 and divided by 2, because 2 positions kind of extinguish themselves. So it's 1,800 geometrical positions multiplied by 9 potential collimator position, and that leaves you to 16,000 combinations, out of which you usually use no more than 200 to 300 beams. So this would be the situation if you look in the inside of the machine. So all yellow points are so-called node positions, which can be addressed by the LINAC, and the LINAC will point to the unit center point. That means at a certain position, all these nodes are addressed by the LINAC, the so-called step and shoot procedure. And after this has been taken place, you have irradiated one part of the lesion. And then the lesion will be moved back and forth, right and left, up and down, and then a different part of the lesion is in the focus. So the target will be moved through the given intrinsic focus. So this is a procedure. You have a making mask procedure. This is a conventional idea. We use a rather thick, rigid mask material. We heat it up in an oven up to 70 degrees, and then we'll pull it over the face. And if the mask is dry, it will leave a face-dependent print. And we use the mask only for CT. We take away the mask for the MRI images because we use a 3 Tesla machine, and we want to use the close-fitting head coils to receive a very high anatomical resolution. And then afterwards, we co-register the MRI images to the CTs. And then on the right side, you see the planning procedure, which is absolutely identical with the approach used by the GammaKnife. You kind of place shots, you place spherical dose distribution, and by methods of weighting the different shots, you can model the dose distribution. You see the different rays intersecting at different parts of the volume at the lower image on the right. And then you fix the patient with the mask during therapy, and you treat. So if you have a look on a typical volume, in this case, the vestibulare schwannoma located on the right side, you see in the middle of the brainstem, and you see anatomically seen right, the cochlea parts which need to be spared. So what you do is you kind of fill in spherical dose distribution in a 3D target volume. And after you've placed the shots, you use different collimator diameters, and you can play and optimize the so-called exposure time. These are the MUs. And then you can perform in a third step a weighting of these shots. If you know there is a critical structure, maybe a nerve, you can say, I would like to go down with the weight with the shots which are close to the nerve. And then in the last step, you can optimize the overall treatment time by looking what beams contribute to what a factor to the overall dose. And then you can partially omit these. And then finally, you receive a dose distribution, which you see on the upper right. Indications to be treated are mainly the same as in all talks given before. We have benign brain tumors, mainly meningioma, vestibulare schwannoma, pituitaries, neurinoma, glomus jugulare, malignant brain tumors, METs, glioblastoma in a recurrent situation, chondrosarcoma and chordoma. You can treat uveal melanoma, as we already heard. We treat rather many AVMs, but that is due to the fact that we have a neuroradiologist which is performing interventions and embolizations in-house. And we treat quite a bit of trigeminal, so-called functional disease. So this is the indication mix up to now. So we have only 8% METs. That's due to the fact we have a lot of neurosurgeons referring patients to our center. So this would be a typical example of a vestibulare schwannoma. You see that the dose distribution, the isodose lines are very, very close to the target. And thus you can spare the organs at risk, in this case, the cochlear parts, which are responsible for the hearing, quite good. These are typical examples. This one was treated a little bit with less dose, only 12 gray, because it was very close to the inner ear, very close to the organs at risk. This is a typical follow-up situation. So we started with 1.5 cubic centimeters at the moment of radiosurgery. After 5 months, we discovered a slight so-called temporary swelling. But if you look in the inside of the tumor, you see that there is some changes, some morphologic changes in the imaging. After 12 months, we have the maximum situation, and from there on, it's shrinking. And it's known that this so-called temporary swelling effect has a dose rate dependency. And since we have a very, very high dose rate of 15 gray per minute, which is roughly 5 times as high as a GammaKnife, we observe that this temporary swelling is a little bit more quickly as which we remember from GammaKnife or from CyberKnife. So a few more examples. So this would be an example if you treat a pituitary device. We distinguish between inactive tumors or active tumors. And we most often use a combined approach so that the neurosurgeon takes out part of the volume transsphenoidal, so it's minimally invasive, and we take the residual part out, which is closely located to the chiasm. And in this combined approach, the results are very nice. So this would be an example of an inactive tumor, so you need rather a little dose of 1 × 14 gray. And this would be a very complicated situation with an active tumor where you have to take a lot of beams in order to prevent side effects on the optics apparatus. This is a MET situation. We have a special situation in Switzerland because we now most often use a so-called pre-resection approach. That means that neurosurgeons decide to take a METS out if it's located at an eloquent situation close to the sinus, like in this example. And then they call us up, and 48 hours prior to resection, we irradiate this tumor and thus sterilizing the tumor cells. And that means during open surgery, there is no danger, no fear of kind of spreading malignant cells. And second, you do not have to treat the resection area. So that is a very nice combined approach. So this would be an example. You see on the right top side that in this case, we treated several METs. This is another example. So you can treat quite nicely. And for us, it's very important that the isodose lines, which carry only half the prescribing dose, which leads to the gradient index, we try to keep the gradient index always below 3, which is a very nice value. Well, that's a classical situation, meningioma. I think we agree meningioma is a very nice indication to be treated by all methods of radiosurgery because it's clearly distinguished, and most often the volumes are nicely feasible for all technologies. This is uveal melanoma, which we treat. We have an in-house idea to not use a frame and not use retrobulbar anesthesia, and no tantalum clips as necessary for protons, and no ruthenium plugs, because we use a suction cap by the company Oraya Zeiss, which is placed directly on the lens, being evacuated by a manual pump. And with this, you have a rigid fixation of the eyes. And the second eye, the healthy eye, is being controlled by an infrared camera. So you have 2 independent devices to control the positions of the eye. And you have a very rigid fixation of the eye, because if you use retrobulbar anesthesia, you have the problem that during the 2 hours where the anesthesia is working, the eye and the bulb can move because the liquid of the anestheticum will be resorbed. So this AVM, that is not very special to methodology, but rather to the definition of the nidus, which is rather complicated. And this is a case which we treat quite often because we have functional neurosurgeons who are very strongly in favor of radiosurgery. So this is a classical chain. You start with medication, and if medication doesn't work anymore, you often end up with a Janetta surgery, which means that you kind of push a piece of plastic in between the vessel, which is kind of knocking on the nerve in order to calm the nerve down. If that doesn't work, often thermocoagulation is the methodology, and if that is not working, radiosurgery. At our center, radiosurgery is already often giving in parallel to Janetta, and sometimes already replacing Janetta. I show you what we do. So these are the two approaches mainly. On the left side, you see the French school. They treat the trigeminal nerve a little bit further away from the brainstem. They call it the distal approach, close to the gangliogasseri. And we use the Pittsburgh concept that we treat close, called with a kiss to the brainstem, obersteinlich-redlich-Zone, where the peripheral nerve system exits to the internal nerve system. And that means there are series that a lot of the pain management is very close to the brain. So we have a procedure that we use a 4 or a 5 millimeter collimator at a distance of half the collimator side to the brainstem. And these are some examples, and you see that we can keep the blue line, which is touching the brainstem, has already a dose which is almost tolerable to the brainstem. And here's an, oh yeah, okay. So that was an example. And now I want to focus a little bit on QA, and I want to go a little bit a different way. If we keep in mind that we all have to accept a chain of uncertainty, and if you look at the different limbs which participate to the chain of uncertainty, I think we all agree that imaging is a very, very crucial point. And the most important point in my experience is the target definition. That means drawing the contours is by far the limb with the biggest uncertainty. The mechanical accuracy on the other side is very precise already now. Patient positioning with frames or mass is kind of, yeah, predictable. We all use a biological model, which is probably explainable, and those calculation dosimetry, as physicists, we all kind of know what we do. So what is the remaining limb which we really have to face is target definition and imaging. And what we try to do, and this is what I want to discuss with you for the last minutes, we use special phantoms with so-called known target phantoms. You see capital crosses, and they have defined geometrical positions within the stereotactic space. So we have these phantoms, and you can put them into either frame, or you can just put them as a phantom into the MRI scanner. And after the images have taken and we have analyzed the center of gravities of these capillary crosses, we go to the application managers, in our case to Siemens, and say, look, these are the deviations which we see. Is there a chance for you to optimize the sequence that we have within our stereotactic space of 10 by 10 by 10 centimeters, roughly, an acceptable deviation? And that's what we do. And we manage, even for a 3 Tesla machine, to be below 1 millimeter in all sequences which we use. That takes a certain amount of effort. That helps us to use, on the one side, excellent anatomical MRI images, on the other, with a credible spatial fidelity. So what we do then, as in kind of an end-to-end test, is we have a special insert into a sphere phantom, in-house sphere phantom. You see this L-shaped lesion with diameters 8 times 8 times 4 is very small, and you can put a film, you see the clearance, you can put a film inside between these two L's and outside. So at the end, you have 3 films. You see the film, or you see the lesion in CT MRI, you can do the best concerning dose planning, no matter of how much time you need. And then you treat the phantom in this case, and then we use absolute dose measurements on the film, and you can see that you not only receive this L-shaped lesion, but even in terms of absolute dose measurements, you have the feeling, okay, you really get what you were planning to, and this gives you additional credibility. So I think for us, it's important that I think radiosurgery has increased. I mean, we all know this. The classical principle of temporal proportioning the dose to the different sensitivity of tissues to radiation is kind of being replaced by geometric portion of the dose into many individual beams. I think we agree that high resolution imaging with high spatial fidelity is essential. The better the imaging, then we can lower the necessary margins. And the overall accuracy of hitting the system is playing the overriding dominant role. And I think that scientific data is documented in many ways. We have heard in the primary talk that in the meantime, almost 1.4 million patients have been treated with the GammaKnife. As far as I know, between 300,000 and 400,000 patients with the CyberKnife, a huge amount of papers. And I think the methodology is valid. In our case, we found out ZAP-X is a dedicated intercalating device. It's a gyroscopic approach, multicentric approach. A lot of pathways are available. It's self-shielding. You need enough height, roughly 3 months, and you need a construction to carry 28 tons. And we really like the very steep dose gradients. And concerning clinical results, so we have follow-ups now from 300 patients. It's totally comparable to what we had with the GammaKnives in the last decades. So we can share, or we have the same results as documented, between 95 and 98% for the benign, and roughly 93 to 95 for the malignant disease. And especially for us, we are very happy that we are integrated in a neuroscience institute. So we are under one roof with neurology, neuroradiology, neurosurgery, and neuropsychology. So we have very small ways to just go one floor higher or lower to discuss directly with our colleagues. So I'm finished my talk. Thank you very much for your attention. I'm open for questions. Thank you.
Thank you, Dr. Mack, for your nice motion. And yes, I have a quick question to you, because your system, ZAP, has the 2 gantry. So I agree with you that the target volume delineation error is much larger than the mechanical or physical error, but we are, as a physicist, we are still concerned about the geometrical and physical error. So I mean, this looks like more susceptible to geometrical error, rotation, because we have the 2 gantries combined together. So can you comment on the isocenter accuracy?
Yes, I can. So these 2 shells are manufactured with an accuracy of 0.03 of a millimeter. And they're so heavy that they're not mechanically driven, but they are driven by a magnetic device. And when we do the daily routine with the Winston-Lutz test, it's not only the isocentric accuracy, so we have a little bit planning inaccuracy on top, and we have a little bit, phantom inaccuracy. But on these daily AQA measurements, it's exactly the same phantoms as used for the CyberKnife. We have an inaccuracy of roughly 0.1 to 0.28 millimeters on a daily basis. This is roughly what we feel. We get an additional uncertainty as soon as we treat a patient. because if the patient is enwrapped in the mask and inside the machine, we can try to calm him down, but he's so excited when everything is moving. When reading out the log files, how much do we have to compensate by the table movement? We see that within the first 2 minutes, the patient is not managing to keep still. You see his eyes moving back and forth and trying to follow the linac. But after 2 minutes, the patient is simply given up. So he thinks, okay, I cannot do anything. I believe I trust the system. And if you look at the log files, there's hardly any movement anymore. Thus, there's very, very little which we have to compensate by the table position.
Great, great. Thank you. And you mean do you have how to monitoring the patient except the CCTV?
Oh,
Do
yes.
you have the KB system, right? KB
Yes, we
X-ray
have the
system.
KB system, and as with the CyberKnife, we are free to choose the intervals between the images, so we can choose. So in the
Okay,
beginning, we have all 20 or 30 seconds, and after we see in the log files, oh, okay, the patient is calm, we can extend the intervals to 60 seconds. So we see the images, we have cameras inside, so we see the patient live. And since the distance from all the devices is rather small and short to the patient, we have a very good idea where the patient is at what time and at what position within the cycle.
Okay, thank you. Now we move to the audience question. So I only found let me see.
It's a question about ZAP-X.
About ZAP-X. And before that, there is a question to Professor Park. It is the number one question is, how do you take into consideration couch rotation error during non-coplanar treatment by using HyperArc?
So, okay, so I already answered in a chat box, but let me explain again. So in HyperArc, actually the MV image must be taken in each of the couch angle, the non-coplanar angle. So due to the geometric limitations, the comb beam CT is not allowed in non-coplanar angle. So as the audience mentioned, since we are dealing with the 2D images rather than the 3D comb beam CTs, we cannot actually 100% guarantee precise the verification of the position. So therefore, when we define the GTP or PTP margins, we allow for some additional margin to account for this issue. And also, whenever we decided the PTP and GTP margins, we also take already account into the value based on the visualist, the tolerance in our center. So basically, we put a 2 mm margins from the GTP to the PTP in our centers. And if you observe any discrepancies greater than more than 0.5 on MB images at each of the non-coplanar angles, we move back to the couch 0 and perform another comb beam CT and verify the patient realignment. From my experience, even though all of the process is very automated with single buttons, but patients positioning tend to really, very stable and very rigid. So from today, I've seen only the one case where the realignments was necessary so far.
Okay, and actually the second question is, he mentioned about brain system. So the reason why he mentioned exact track is that because brain lab has to separate the imaging system. So I'm sorry for we don't have enough time to include brain system in this talk. So I'm sorry for that if some audience they are using brain lab system. And let let's move to next question. So could you answer about the ZAP-X system, Professor Mack? Can you look at the chat window?
Okay. So what are the questions?
The question from Yoon-So-ji, she mentioned about a vendor provided paper mentioned that the last question in the chat box. Can you see that, Professor Mark?
Thank you. Last in the box was, we are currently separated plan for cases for multiple targets. Is there a more efficient way to?
Actually, she had 4 questions. The first
I have all
one
questions, yes.
Yeah, the first one is regarding the shielding.
Yes. And workload. But I cannot understand what exactly she wants.
I mean, I think the leakage radiation is more than the paper. That's what she is asking now. So extra shielding might be needed, might be necessary.
Okay, now I see this. A vendor that workload is okay. Gantry angle is automatically adjusted for each treatment pass. Is there? Yeah. What I can answer here is there is the option to generate individual pathways. According to different pathways, you can address more out of these theoretical 16,000 combinations. And the manufacturer is offering certain pathways for classical indications. And then you can, as a customer, say, okay, we have a majority of functional lesions which we want to treat. We want to have additional node positions which are automatically involved into the optimization. So we have several individual pathways which we gave to ZAP, and they addressed these points for us, and they are determined as belonging to a special pathway for trigeminal cases or vestibular. So you can individually automate several pathways to optimize.
So I guess it's very, very specific to ZAP-X system. So why don't you communicate each other after this webinar? So,
I'm happy.
yeah,
Absolutely. Thank you.
Yes. And because we don't have any other question and comments from audience, so I just ask you as the speakers, if you want to mention something, comment, then we can discuss each other.
No.
Could you, Professor Chung, could you mention something?
No, I
No.
have no more talk.
Because I found that from the Professor Mack presentation, there is comparison between the GammaKnife plan and HyperArc plan. What is your?
Every radiosurgery devices are trying to compare their machine with GammaKnife, but it is performed by their own work. If you want to compare, more objective way, someone else, the third party, should do it. That's all I can say. Because the treatment planning, the quality of planning depends on the planner very much.
Right. And then I guess that's the benchmarking test done by the Professor Park to how they can achieve that with a HyperArc plan compared to GammaKnife plan. So
okay, let me comment on that question. Actually, we have the GammaKnife center in our institution. So we actually exported all the CT data to the GammaKnife team, and also there is also one of the physicists working for that centers. So we asked them to, do their plan in their work. So after plan that, we collected all the data from the GammaKnife system. They're also using the icon system and collect it back to the Eclipse and compare with the HyperArc techniques. So as you mentioned, it's very dependable, depends on the planner style and their experience. And so of course it might have some, some differences according to the experience.
Let me add one thing. If it started, the plan is plan.
Yeah,
The
yeah,
thing
plan.
we need to compare is the actually irradiated films.
Mm-hmm.
So I think
Yeah.
the plan is plan.
Yeah, the plan is planned, and we just assumed that and calculated the demo time between the GammaKnife and HyperArc.
And I agree that GammaKnife takes a long time, but one thing I want to more say is the preparation time for GammaKnife is nothing at all. If a
Yeah.
patient come in the morning and the neurosurgeons decide to perform a radiosurgery, if absolutely necessary, we can start GammaKnife surgery in the afternoon.
Yeah, I totally agree.
But it's not possible with Linux, I know.
Mm-hmm. Yeah, we still need to check a lot of, the stuff.
Yes,
before
it
we
is
get into-
important for malignant tumor patients.
Mhm. Sure, yeah, that's true.
How about Professor Hojin Kim? Do you want something to comment?
I think most of the questions were already answered by the speakers. So I have not clear, question and something to be discussed here.
Okay. Then Professor Mack, do you have something to comment?
No, I would just like to add this last topic. I fully agree with Dr. Chung that it does depend on three things mainly. It's the methodology technology itself, on the software, which is embedded in the planning system, and then on the experience of the user. So what is not possible at the moment and which would be necessary to deliver a clear picture is to have a totally independent planning system, which could kind of, calculate on an automated basis with all technologies. Then you would have something which is independent of the bias of the user, which is independent on the bias of sophisticated software, and then you can really drive the methodology to its limits. Otherwise, it's different. You can just give ideas, perspectives, but you really don't know exactly. That's my feeling. And the second point is, I think, from a physics point of view, we are not the weakest link in that we are sophisticated. I mean, what we can do in terms of dosimetry, what we can do in terms of experience. But the vast problem is the contouring. So, I mean, what we did in-house is a sophisticated program that means we start with defined windows in which we draw in the contours. These threshold windows, contrast enhancement, they are standard for all doctors. All doctors start T2 base because we don't want to exaggerate the volume. And then in a second stage, we fine tune with imaging using contrast enhancement and all these things. I think these limbs we have to focus much more because there is by far the biggest uncertainty in my belief.
Yes, that's correct. There is a study, spread the MR images to all over the world and let them draw the ABM lesions. And she found there are about 3 times difference in the definition of ABM.
Yeah.
That's the worst case, but anyway, she found. So lesion definition is very important, of course.
Yeah, I guess that's the reality, right?
Yeah.
Okay. Thank you for the all audience, and thank you for all the excellent speakers to take your time also to prepare the presentation and give us the excellent talks. And all the audience also, thank you for staying here Saturday. Hope you enjoyed this and this webinar, and enjoy the rest of the weekends. Mary, could you have some comment, last comment or announcement?
No, I would like to thank all of you. It was a wonderful session, very informative session on navigating the landscape of brain tumor surgery, comparing GammaKnife, starting from the very basics to the high-end thing which we are utilizing today, GammaKnife, CyberKnife, HyperArc, and ZAP-X. Thank you so much. Thank you so much, Professor Byungchul Cho, for moderating this session. And thank you, Professor Chung, Professor Park, Professor Kim, and Professor Mack for the wonderful talks you delivered. And thank you all the participants for joining. And until we meet next time for the next webinar, bye to all of you. Thank you very much.
Thank you. Thank you all.
Bye.
Bye. Thank you.